Hey, all right. So, the last week-ish, the last week and a half-ish, um, what we need to that sounded like I said the last week and a catfish, which is not really what I meant. So we're gonna talk all about hearing this week, and what better way to start it off than talking about hearing anatomy? Um, so, I mean, let's jump into it. Um, the first thing I want to do, I want to start off by talking about sound. I mean, we can't really talk about hearing without talking about sound because that's what you're perceiving. Remember, all the way back towards one of the first lectures that we had in the course, what happens here? What happens when you're making sound? What happens when you're speaking? Well, your vocal cords, your vocal folds, are going to create little puffs of air. And those create sound pressure waves in the air. When your vocal folds open, the air comes out, it's more compressed here, and then that gets pushed up through the pharynx, through the mouth, the oral and the nasal cavity, and then comes out of your mouth as a sound pressure wave. When the vocal folds are back together, then you don't have that high pressure zone. They come apart again. You have high pressure, back together, low pressure, high pressure, low pressure, high pressure, low pressure. And what this does, it sets up a vibration. This is then what we shape with our effectors, our pharynx and our oral cavity, and then whether or not we're letting air into the nasal cavity. And then that all comes out as a sound. It's still a sound pressure wave. So really it's just sound flowing through the air. These waves, these areas of more condensed air molecules or less condensed air molecules. That's what sound is. And this is why things like explosions have a sound, or why clapping your hands has a sound. It's not really, there's nothing here that's creating a sound. What's happening is I'm hitting my hands together and it's forcing the air out in this large kind of gust of wind, sort of. You can feel it, right? When you clap, you can feel air hit your face if you clap really close like this. And that's what's making the sound. It's that pressure wave that you can feel on your face. That's the sound. You create this like large pressure wave, this sound front, that then reaches your ears or the ears of whoever you're clapping for, and is sound. And that's true for all other things that make sound as well. Right. We talked about, I'm trying to remember if what I'm going to show you in these videos is what I'm going to explain to you. I don't think it is, so that's okay. So a guitar string is, you're just going to pluck it, right? And it's going to vibrate. And what happens is that vibrating string pushes on air. If it's an acoustic guitar, there's the sound hole inside which resonates the sound, the little bit of sound that's the little bit of air pressure wave, the sound pressure wave that the string is able to push. It resonates inside the guitar and it creates a much louder pressure wave. An electric guitar works in a slightly different way, actually. I mean, if you have the guitar turned off, you hear just what the vibrating string sounds like. If you have the guitar turned on, there's actually a magnet in the pickup, and it is going to make a frequency based on where the string is over that magnet. So that functions a little bit differently, but the acoustic guitar is all sound pressure wave. All right, so I was going to talk about microphones and stereos, but I've actually got these YouTube videos about them, so let's just take a look at those.
At 1-800-CONTACTS, we're here for Allison, whose prescription just expired. Don't worry, Allison. With our express exam...
All right.
Hello, YouTube. I hope you find this video entertaining as well as...
All right. There you go. So what you're seeing here, here's a subwoofer. And what this guy's doing is he's going to put water on top of it. And this is going to help us visualize what's actually happening. There we go. So this is kind of a low frequency wave. And you can, what's happening is we might not even be able to see this with our eyes, this vibration of the subwoofer, but the water in here helps us see it. That's low frequency. I think they're going to turn it up to high frequency now. Yeah, I've watched this a lot of times. And this is getting more intense, louder. There's larger vibrations if it gets louder. Same frequency of vibration, but larger. So this would be maybe, you know, a quiet vibration, a really low frequency quiet vibration. And then this would be loud, but same frequency, because we're moving up and down at the same speed. What you're looking at here, this is a very high frequency at a pretty low to moderate intensity. This is getting louder. You can see that the water then starts jumping all over the place the louder you get it. But the vibrations on the surface of the water is pretty much exactly like what is coming into the air. The only difference is that the surface of the water that you're seeing here, this is a two-dimensional wave. But air is like a three-dimensional wave, right? It's all over the space. And now that the subwoofer is like down inside a much larger amount of water, it's going to function a little bit more like a 3D wave. But the differences are kind of like on the surface, you know. I mean, we can really visualize what's actually going on. You just have to think of it as coming all out from all areas of the sound. I'm talking, and these waves are coming out from my mouth in all directions, not just straight out. So this is pretty amazing, right? This is just the vibrations. This is what the air looks like. If you could see the air as it was traveling towards your ears, this is what it would look like just from this subwoofer. I don't think... Yeah, okay. Well, here's another picture of a 2D wave. So this is pretty much all I wanted to show you in this video. Let's see if anything interesting happens here. They're going to put the duck in the middle. All right. Anyway, that's pretty much it. This will be up so you can take a look at it if you want to watch the whole video. It's entertaining. It's really, I like it. It's a good video. Okay, so now the next one should show us... I think it's just cymatics, like dust on a plate. No, it's not. Sorry, I'm lying to you. Alright. Sorry about these ads. Okay, so this is pretty amazing. So what's going on here is they're going to hook up a loudspeaker to a hose so that it vibrates at 25 hertz, I think. 24 hertz, okay. And what's going on is their camera is also set to 24 frames per second. So what's happening is the camera is capturing the vibrations of these these droplets of water in exactly the same place. If we turned up the frame rate of the camera, you would see it, you know, jumping around. But because the frame rate is exactly 24 hertz, it kind of freezes it in time. Now, what's going to get crazy, you can kind of see this if you look at the dude's hand and other things. Like, it doesn't look quite smooth enough. Like, it doesn't look like TV quality or even, you know, this quality that I have on my video. So if the water is slightly out of sync, if the vibration of the hose is slightly out of sync with the video, it's going to look like it's moving forwards. And then what they're going to do is they're going to make the vibration be out of sync with the video in a reduced capacity. So it's going to be 23 hertz with a 24 hertz camera. And that is just phenomenally weird. I'm not going to give it away until we get there. Yeah, here we go. It's reverse effect. They give it away already. Look at this. They haven't reversed the footage. This is just because the frequency of vibration is just slightly out of sync with the frame rate of the camera. All right, so now we're going to take a look at, this is going to be waves with sand on metal plates. So this is called cymatics, what we're going to look at. And what basically that is you have a metal plate and you shoot a sound through it, different frequencies of sound. What happens is the different frequencies are going to resonate differently with there we go. The different frequencies are going to resonate differently with the metal plate. And what that does is it sets up different places where the plate moves or doesn't move. And if you think about sound, we talked about nodes and antinodes. So if you have a string, you have a node at one end. Think about a guitar. There's a node at one end and at the other end. The string doesn't move at that node. It moves everywhere else. It can go in a complete arch from node to node. But if the frequency increases, that can also become two arches. You could have it so it bends down and comes back up and then arches over to the other one. There's pictures of that in the earlier slides if you want to go back and look, but you'll have this sine wave, this perfect sine wave. In the middle right here, even though the string isn't held down, that's a node. If you were looking at the string vibrate, if you could slow it down or use a 24 hertz camera just to watch this guitar string, you'd actually see that, over here, the string is going to go whoop, 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 and then over here it's going to do the same. So it's going to go like that. But right here in the node, it stays perfectly still. So what you're going to see is that there are nodes and antinodes. Antinodes are just the part where it moves most maximally. You're going to see nodes and antinodes in these metal plates. The sand is going to collect in the nodes because the metal plate isn't moving there, and the sand is going to move away from the antinodes, the parts that vibrate a lot. And again, like I said, different frequencies are going to set up different patterns of nodes and antinodes. One thing that I want you to keep an eye on is the fact that the nodes will stay. So a node at 400 hertz will still be a node at 800 hertz, but there will be more nodes. So our nodes are these swooshy things, and at 800 we don't see that again, but if we go to a multiple of 300, we'll see those swooshy things again. So 498 isn't a multiple of 300, but I guess we'll just have to wait. It's amazing though, isn't it? It's just sound vibrating a metal plate with sand on it. the number of nodes grows with the increasing frequency, and that's because your string is vibrating more quickly. There's going to have to be more nodes to take up more of these antinodes. And that's what you're seeing here. There's just more and more and more nodes as you climb in frequency. And this one's going to be pretty much the same thing. She's just using 2 different colors, so it looks way more trippy. But it's it's the same story. You'll see some of the same patterns emerge. And that's the end. All right, cool. So that's waves. Let's jump back to our slideshow here. There we go. Here's waves. These are just waves in water. And you know, again, that's a 2D wave. We're usually talking about 3D waves with sound. But the analog is good. They make sense with each other. All right. So let's talk quickly about frequency. The frequency of the sound. Frequency is also related to pitch. So frequency is what we measure, like how often the wave repeats itself. That's the frequency. That's the definition of frequency. Pitch is our perception of frequency, which usually goes hand in hand with what the frequency is, but it can change based on some other characteristics. We'll talk about that in a future video, but just know that pitch is our perception of frequency. They usually go, parallel with each other, but some things can change that. So when we measure the frequency, we usually measure it from either peak to peak, nadir to nadir, or you can go from zero crossing to an identical zero crossing. Remember, there's multiple nodes. You have to go to the identical node if you're going to measure the actual distance of a wave. So, again, one wavelength is peak to peak, or it's nadir to nadir. It's the same distance, or it's the zero crossing to the identical zero crossing. That's one wavelength. The higher the frequency, the shorter this wave is going to look. Like it's going to compress all this down into a small amount of space. So there's going to be less distance covered by one wavelength, or one wavelength will happen in a much smaller amount of time. And actually, that's how we measure frequency, is how many waves can be repeated in 1 second. So we also call that cycles per second. Cycle is just one wave, the cycle of one wave, and it's measured in hertz. That's just what cycles per second is, which is abbreviated as Hz. It's really important to note that frequency is a linear scale, but our perception of frequency is not linear. So if you think about, if you're a musician, you'll know this. You probably know this already. But concert A is 440 hertz, which means there's 440 cycles of a wave per second. Well, what's the next A? Do you know the frequency of the next A? It's 880. So there is 440 hertz between both of those A's. So the question then is, if our perception is linear, which it's not, but if our perception was linear, then we would expect that there's one A at 440 hertz, then we jump 440 hertz to 880, and then our next A, if it was linear, would be 440 hertz away from 80. Now I have to do mental math that I wasn't prepared for, so that's not great. 20, 12, and then you carry it, and so it's like 1320. Yeah, I think that should be right. So 1320, it should be 1320 hertz if it was linear. But the musicians in the class are probably yelling at the screen. No, that's totally not. It's not 1320. is not the next A. So what it is you double the frequency to get to the next octave or to get to the next A. So it's 440 hertz, then it's 880 hertz, and then you then add 880 hertz to it, which would be more mental math. 1760. And then the next A up from there, you add 1760 onto that, which I'm not going to do. I'm not going to do that mental math right now. You get the picture. If we did it in a much more easily understandable way, 100 hertz, the next octave is 200 hertz. But the next octave from there is 400 hertz. And the next octave from there is 800 hertz. So you do this doubling. And that's when we hear a consonance between the sounds. The sounds come back around to make the same consonant, harmonious sound. And so that's how we know that our perception is logarithmic. But the actual frequency of a wave we can measure on a linear scale. This is kind of like color. We can measure the wavelengths of color, and it's a linear scale. It's just, it goes on up. This is where color is. But our perception of color is circular. The color wheel. So our perceptions don't always match how we measure these things. Things are usually travel on a linear scale, but our perceptions of them are not necessarily linear. Color is circular. Frequency is, or pitch, I guess. Pitch is helical and also logarithmic. So it's an interesting way to perceive things. An interesting distinction between what our perception is and what the actual scale is. The amplitude, this corresponds to loudness. So it's just how loud something is. Amplitude is the actual amount, the actual height of the wave, and loudness is our perception of how loud it is. This is a lot like frequency and pitch. So usually loudness and amplitude go right along with each other. They're parallel. But some things can influence us to think that something is louder or quieter when the amplitude is the same. And like I said, we'll talk about that later. But essentially, amplitude is just the height of the wave. So if you look, do I have a thing? No. Okay. This is just the height of the wave. So from this 0 point right here up to where the wave is, that's the amplitude. So from 0 to where the, this yellow arrow is pointing, that's the amplitude. That's measured in decibels, which is also a logarithmic scale. So our hearing is logarithmic both in terms of pitch and loudness. And we'll talk more about our hearing scale and which decibels are audible, barely audible, damaging to your hearing. And I think you'll see what I mean by a logarithmic scale. So phase, we'll go over this quickly. This isn't super important. A phase is just where a wave begins. Waves in the real world usually start at 0, and because they're moving towards compression. Why is that? Because you have to start with nothing. When I start talking, there's nothing going on. There's equilibrium. And it moves towards compression because I can't suck air out of my throat somehow. I'm talking, and so air is coming out. So it's going to move towards compression first. So this is exactly what a wave is going to look like. It's going to start at 0. It's going to move towards compression. You can digitally make a wave that doesn't start at 0 and doesn't move towards compression, except here's the thing. Your computer is going to have a hard time figuring out what that means. I mean, it's going to move its microphone back, I guess, and then it's going to push it forward. So really it's not going to create sound until the wave goes into compression again, and it's going to start moving. So it is going to be, you will change the phase overall, but it's still really going to start the sound at compression. Anyway, it begins at 0, it moves towards compression. We can use phase to determine where a sound is coming from. So if you think about this, like let's say my head is right here. It's this circle that's taking up about this zone right here. Well, so my right ear is going to be right here, and the phase at my right ear is going to be right here. It's still negative and it's moving towards positive, but it hasn't crossed the 0 line yet. And at my left ear, which is about right here, it's past the 0 point and it's moving towards positive. So I have a different phase at each ear. And this can help me figure out that the sound is coming from over here. But usually we don't actually sense phase. That's pretty much the only time we do actually sense phase is as part of our localization system. There's a lot of other things that we use, like the onset time between ears, level differences between ears. You'll learn all this in hearing science, but then also phase difference between ears. We use all that to figure out where a sound is actually coming from, and other cues as well. It's a complicated thing, localization, but phase is one property. Okay, so one thing that you should know about sound waves is that they're additive. You can put them together. A wave with an amplitude of 15 added to a wave with an amplitude of 15 makes a wave with an amplitude of 20. No. 30. Mental math. So an amplitude of 15 plus an amplitude of 15 equals an amplitude of 30. Because they're additive, they can also cancel each other out. If you put a sine wave that's off phase, that's completely out of phase, they'll actually cancel each other out. So here we've got plus 15 amplitude, and here we've got minus 15 amplitude. And now here it's plus 15, but down here it's minus 15. So if these are additive, positive 15 plus negative 15 equals 0. And everywhere along this timeline of this wave is going to equal 0. This is how noise cancellation works. Well, this is how some kinds of noise cancellation work. Active noise cancellation works this way. It will sense what frequency is, most prominent in the environment, or frequencies, and it'll play these out of phase, and you don't hear the sound anymore because they've been blocked out. There's a really, really amazing museum exhibit in Germany where what they've done is they build like a sound isolation booth, but there's no walls. It's all done with sound waves played out of phase with the other sounds of the museum. So outside the sound booth, you hear everything. But you walk inside the sound booth, and they've just got microphones arrayed so that they're shooting out sound that's exactly out of phase, 180 degrees out of phase, with the other sounds in the museum, and you can't hear anything in there. It's like you're in a silent room. You can see people moving their mouths, but you can't hear it. It's so cool. Okay. So a pure tone is a sine wave. We talk about pure tones a lot when we talk about sound, because it's the basic building block of sounds. One pure tone is just a sine wave, and a sine wave sounds like this. Clearly that's not what a sine wave sounds like. I clicked on the wrong one. Okay, that's also not a sine wave. A sine wave sounds like boo, boo, kind of like that. They can make up, well, and this is a sine wave here. I should say that. This is a perfect sine wave. This also is a perfect amount, perfect representation of compression and rarefaction, which is what the opposite of compression is called. And so the theory of sound is that all sounds are composed of multiple sine waves working together. My vocal folds vibrating, so there's the puffs of air. There's also different ways that the vocal folds actually like vibrate from top to bottom, along, you know, the course of each other, and then also the frequency that the puffs of air come out. These are all different ways that it can create different vibrations, which gives it a few different, you know, sine waves that are coming out of just this one sound that I can make with my vocal folds. So a sound, any sound, is made up of a collection of sine waves. Because it's just oscillations in the air, right? If you think about a sound pressure wave again, it's just pushing against air and it's moving, and then there's areas where there's lower pressure. So it's just high pressure, low pressure, and just those fluctuations. So if we want to change that, if we want to make that more complex, we add something in that makes that fluctuate in a different way. So we have high pressure, low pressure, high pressure, low pressure, but then you can add something that goes high, low, high, low, high, low, high, low to that, and they'll sometimes cancel each other out, but sometimes add together to create a much louder, a much stronger pressure wave, and then that creates a complex tone. That's a combination of multiple sine waves. Well, so if this is true, then we should be able to use math to decompose sound into their constituent sound waves, their constituent sine waves, rather. And that's true, we can. Down here in the bottom right-hand corner, this is a Fourier transform. So this right here, this is me saying so So now I can actually play this for you. That's me saying so And this is what it looks like if I record the whole thing. This is just the waveform of me saying so This is the O portion of so I've highlighted the O portion, and I want to see what sine waves that's made up of, because every complex sound should be made up of multiple sine waves. And so this is what we have. We have energy. This is showing that there's a lot of energy at this frequency, this frequency, this frequency, this frequency, this frequency. Every peak shows where there's a lot of energy. And so that shows that this O of me saying so is made up of energy, a sine wave, at each one of these peaks. And the height of the peak is telling me the amplitude of that sine wave. So we can actually see how to recreate my O. Would be just to make sine waves at these different amplitudes at these frequencies. So that's complex sounds made up of many, 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 many sine waves. The sine wave is the basic building block of all complex sounds. Again, so is a disfluency that I say a lot. I know that. And so when I recorded this, I decided that I was gonna like remix my disfluency. So that was what I did before I made this, while I was making this lecture. No, we don't want to hear it again. Okay, so let's talk about the outer ear. Let's start talking about the outer ear in the very next video. So this is the end of this video, and we're going to move on to the outer ear and the rest of our hearing anatomy next.